Here's the regression model. Notice that I'm no longer using double lines for the vectors and matrices. This is just easier and cleaner to read. And at this point, you just have to keep in mind that everything in sight is a vector or a matrix, unless we say otherwise. The dimensions are, as you will recall. And now we're focused on beta, the vector of parameters, and these are fixed numbers. We just happen not to know them, and we want to estimate them. In the end, it's not beta that we want, it's y. Right? It's the response. So the point of estimating beta is from that we are going to estimate y, which is the response, and that helps us describe the data that we have or predict the response for a new individual. So in this section, we are going to set up a motivation for what the formula should be for the best estimate of beta. And then we'll proceed to actually establish that that's indeed the best in the sense of least squares. So here's some notation. The best estimate of beta, we're going to call that beta hat. And in the end, we want an estimate of y. So the corresponding estimate of y, we will call y hat. And that is going to look up at the model. Beta we are replacing by beta hat. So we're going to have x times beta hat instead of beta. And of course, there's epsilon as well. It's a random error that we don't get to see. That we can estimate by 0, because that is by assumption of the model mean zero random vector. And so to see how to get at the best estimate of beta, we need to think about the error in the estimate, which you'll recall is called a residual. We're going to call that E for error, and that's y minus y hat, which is y minus x beta hat. And just because this is the first time I've written down E and it's not your friend the exponential, I'll write down that E is an n cross 1 vector of observed errors. And we somehow want E to be small, or we want y hat to be as close to y as possible. And y hat has to be a linear function of x. So how do we choose beta hat to make this happen? We can start by noticing what linear functions of x look like. This is a function of the form x times gamma, where gamma is some p cross 1 vector. Now, we'll use a visual image that we have used before, which is the space of all possible predictors is the space of all x gammas. Just vary gamma across all p cross 1 vectors. And we'll think of that as all falling on the surface of a table. So as you vary gamma, as you vary the coefficients, you get different linear combinations of the x's. Now, y, the response, is actually not on this surface. Y is somewhere else. And our goal is to find the point on the surface that is closest to y. That is y hat. So where is it on the surface? We've seen this idea before. We just simply drop a plumb line from y to the surface. In other words, we get the projection of y onto the surface, and it's this foot of the perpendicular. Let me use a nice bright color. That is y hat. And so, of course, since it is on that surface, it is x times something, and that something is what we're going to call beta hat. So the defining property is that this is the projection of y on the surface, and so in other words, this vertical distance, so that is the error, that is orthogonal to the space spanned by x. And so this is the main idea behind the estimate. So that is the geometric picture, and it is the same as the picture you saw when we discussed the conditional expectation as a best linear predictor or least squares linear predictor. Here the algebra is like this. Orthogonality means the dot product is 0. In other words, x transpose E is 0. Now, what's x transpose E? It's the error, so y minus y hat is E, and y hat is x beta hat. So I have x transpose y minus x beta hat. So if this is going to be 0, then can we isolate beta hat? We're trying to figure out what beta hat has to be. So I can see that then x transpose x beta hat has to be x transpose y. And now, if we could only do the following, which is multiply both sides by x transpose x inverse, then we will have isolated beta hat. We'll have a formula for the estimated parameters. And this works provided that inverse exists. Now remember your linear algebra. This happens when X has full column rank. And what does that mean? That means no column of X is a linear combination of the other columns. So we're going to assume that condition. Now, is that a reasonable condition to assume? It is a very reasonable condition to assume in our situation, because we are trying to predict Y based on a linear combination of columns of X. Apart from noise, our model says that Y is a linear combination of columns of X. Now, if you're going to take linear combinations of columns of a matrix, why would you have that matrix contain columns which are already linear combinations of the others? It doesn't make any sense. You don't gain any information from those columns. At a very extreme level, you wouldn't predict weight on height in inches as well as height in centimeters. You would use only one of those two columns. And so we will assume that when we do our analyses, the columns of X are linearly independent of each other. That is, no single column is a linear combination of the other columns. And in that situation, we have guessed a formula for the best estimate of the parameters. It's still a guess. We haven't actually said this is the least squares estimate. So you have to do a little argument to make sure that that is indeed the least squares estimate, and that is in the textbook and you can read it. It follows very, very easily. The main thing to remember, of course, about the regression estimate, just as with conditional expectation, is that it's a projection onto the space that you want.